Hello everyone, welcome to my YouTube channel Victoria Physics. In this video I'm going to discuss about operational amplifiers. Let us begin our discussion. The very first question that comes in our mind is, what is an op-amp? The term op-amp or operational amplifier refers to an amplifier that performs mathematical operations. Historically, first op-amps were used in analog computers where they did addition, subtraction, multiplication, etc. Earlier, op-amps were built as discrete circuits. Now most op-amps are integrated circuits. So, operational amplifiers are able to amplify a signal due to an external power supply. The name derives from its use to perform operations on a signal. Hence, operational amplifier is a very high gain differential amplifier with high input impedance and a low output impedance. We will go into detailed discussion on this differential amplifier later on, but for the time being, just let us concentrate on the basics of operational amplifier. So it's a low-cost integrating circuit that consists of transistors, diodes and resistors, which are the only components in a typical IC. Capacitors may be used, but they are small, usually less than 50 picofarads. You can see over here there is a capacitor which is around 30 picofarad that is being used here. For this reason, IC designers cannot use coupling and bypass capacitors the way a discrete designer can. Instead, the IC designer has to use direct coupling between stages and also needs to eliminate the emitter bypass capacitor without losing too much voltage gain. The differential amplifier is the key. The design of this circuit is extremely clever because it eliminates the need for an emitter bypass capacitor. For this and other reasons, the differential amplifier is used as an input stage of almost every IC op-amp. We'll see this when we'll discuss about different stages of an op-amp. Let us learn the symbols of an op-amp, about the symbols and how they appear. At present, a variety of op-amps are available, almost all in IC forms, and are sold relatively at low price. An IC is a complete functional block with external pins. As you can see over here, there are pins. By connecting these pins to supply voltages and few other components, we can quickly build up all kinds of different useful circuits. This very figure shows the standard circuit symbol of an op-amp. Well, due to its popularity in electronic industry, op-amps are available in different packages such as 8-lead dual line package, which is abbreviated as TIP, with 2 parallel rows of pins, and also TO5 metal case with circular array of wire leads. The metal case is costlier than TIP. So this particular figure shows the pin diagram of an op-amp IC741, which is in 8-lead dual inline package format. So the pin numbers can be easily identified by holding this IC with the pins downward, and the identification mark or the cut mark, this mark, in the forward direction as shown in this particular figure. So there may be a dot as well. This is pin number 1, so you can find a dot near pin number 1 as well. The plus voltage and the minus supply voltage are connected to pin number 7 and pin number 4 respectively. For IC 741, usually plus minus 12 volt or plus minus 15 volts are used. No connection is required in pin number 8. Pin number 2 and pin number 3 are the input pins. Pin number 2 is known as the inverting input pin, and pin number 3 is known as the non-inverting input pin. If a signal is applied to the terminal 2, then what happens that the output will be 180-degree out of phase with respect to the input. On the other hand, if a signal is applied to the terminal 3, there will be no phase reversals. Pin 1, pin 5, both are used to make offset null arrangements. For more information on offset null, you can see the link in the description box below. I guess the pin configuration of 741 IC is clear to you. Now let us move on to the block diagram of an op-amp. The internal circuit diagram of an op-amp is very much complicated, involving many active and passive elements, as you saw in our previous circuit design. I'm going to tell you about the architecture employed by majority of commercially available op-amps. Okay, so there are 4 different stages. Let us begin. I hope the picture is clear to you. Well, the first stage is the input stage. It is used in most op-amps, and it is the differential stage with 2 inputs and a double-ended balanced output. This amplifier configuration establishes many of the IC's input characteristics. It provides the inverting, non-inverting inputs, the high voltage gain, high input resistance, and also high CMRR. After that, we get the intermediate stage. It is also another differential amplifier with 2 inputs and a single-ended unbalanced output. Number of intermediate stages may be varied according to the requirement and keeping in conformity with the operating conditions of the amplifier. Moving on to the next stage. As I said earlier, that since large capacitors cannot be fabricated on a chip, the gain stages are directly coupled. Due to direct coupling between the intermediate stages, the base inputs successively rise up to such a high level that it requires to shift the input voltage level back to get an output level at a 0 output corresponds to 0 input. This is accomplished by a DC level shifter. I hope up till now it's quite clear to you. I'm moving very slowly so that you can follow what I'm trying to say. So the final stage, we reach the final stage. This stage consists of a push-pull complementary amplifying system. This stage not only produces a large output but also raises the current supplying capacity of the whole amplifying system. So the block diagram of an op-amp gives you a picture as how it operates. So the equivalent circuit of an ideal operational amplifier would be somewhat of this nature. So you can see there is an input section, we have a differential amplifier section, followed by a gain section, and final stage is the output. Over here, in an ideal op-amp part, few things you have to remember. An ideal op-amp is characterized by the following features, that the input impedance, as you can see over here, the input impedance must be infinite. The output impedance must be zero. It is also characterized by infinite voltage gain. These are some of the major characteristics of an ideal op-amp that you should remember throughout our course on operational amplifier. Some more points are also there, that the bandwidth should be infinite. The slew rate must also be infinite. I'll go into detailed discussion on what is slew rate and how to calculate slew rate. The CMRR is also infinite. You can learn about CMRR in my another video tutorial. Just go to the link below in the description box. And well, these are some of the characteristics which are very important in case of an ideal op-amp. Also, the characteristics do not drift with temperature and has a perfect balance. Perfect balance, I mean to say, is that the output is zero when two of the inputs voltages are equal. So few points to remember about ideal op-amps. Just to recapitulate a bit, this is the symbol of an op-amp, that is the inverting terminal, and this is the non-inverting terminal, and there goes the output, which is connected to pin number 6. We have inverting voltage and non-inverting voltage. Since the input impedance is infinite, I just said about the characteristics, so we get I plus and I minus to be equal to 0. Also, as the gain is infinite, so the voltages around this terminals would also be equal. Finally, as the output impedance is 0, you should remember that the output voltage must be independent of the output current. Well, op-amps are used in many applications. They are made into inverting amplifiers, non-inverting amplifiers. There are simple amplifiers. You get adders, subtractors. Adders are also called as summing amplifiers, and you have comparators which can compare given values. Also, you have integrators, differentiators, Smith triggers. I'll discuss all of this in my tutorials. Thanks for watching. Did you like this video? Then give it a like and subscribe to Victoria Physics for more learning materials and videos. Stay at home and stay safe. Thank you.